by name by Madam. My name is Nandakumar. Okay, and I have been working in the as head of the department in electronics in the Biodas University, followed by in the Northumbria University. Then I moved to the Intel and worked in the Intel for 4 to 5 years as a silicon validation engineer. And now I'm working as a professor in the University of Nottingham, where I started my career as an assistant professor. So this is my short brief about where I work. And my research interest is in digital VLSI design, test, fault, the test and defect fault tolerance in digital systems, emerging non-volatile memory, approximate computing, and recently I embarked on a neural. So with this introduction, I would like to take you into the objectives of today's lecture. So when I see the module structure itself, there are some aspects that actually covers on the programmable logic device. That's from the last unit. So this basically covers PLA, PAL, CPLD, and FPGA. So this is a topic that's been actually in your modules. PAL, CPLD before I really jump into an FPGA. So today's class will be like planned for like 1 hour 15 minutes like that. Okay, and we'll be touching these areas, and we will be moving on to the FPGA. Maybe we'll be touching more on FPGA and its internals and how does it actually program, and what are the things that we need to take care when we actually program FPGA. And also we see some of the applications in terms of bus protocols. That means that we will actually do a simulation. You will design so-called protocols. Maybe you might have used it during your Raspberry Pi or some microcontrollers, some of the protocols. So we will try to actually design those kind of protocols, and then we try to implement on the FPGA and try to see whether those protocols are working. Okay, so that extent we will actually go through this FPGA part. But for time being, I will actually touch the PLA, PAL, and CPLD. Then I will move into FPGA architecture, a general architecture, which is an SRAM-based architecture. Later, I will actually show you the other architectures of FPGA as well. The final idea is I want to introduce some of my topics, which is non-volatile LUTs for FPGAs, which is my research area. Currently, we also developed a non-volatile FPGA architecture. I can also talk about this, but that is more towards your research or when you want to do some kind of a project. So I will talk about non-volatile FPGA architecture. Okay, so with this introduction, I just go into the programmable logic devices itself. I hope you all can see my screen and hear my voice clearly. If you don't hear my voice or my screen, see the screen, please do let me know. Okay. Um, Most of you would have learned during your undergraduate or during your first year or somewhere about these programmable logic devices, which can be actually split into two. One is factory programmable device, and another one is field programmable device. Okay, I'm talking about the field programmable
Sir,
device.
excuse me, can you put it in the slideshow? Slideshow?
It's in the slideshow only, madam.
Some slideshow.
Are you not seeing the slideshow?
Have you moved the slides? Have you moved the
Hello.
slides? Sir,
Yeah,
have you moved the slides or in the first slide itself?
I moved already the slides.
Okay, we are not seeing any change.
Okay, let me see why it is like that.
Maybe you can stop sharing and again do it. Yeah, told her.
Are you able to see now?
Yes, sir. Yes, sir. Yes, but it's not in the slideshow, I think so.
Okay, Because of this
Okay.
Google Meet, is it not in the
So
slideshow?
we'll put it in full screen, sir. Here, it will
Hello.
happen.
It, I think it's in the slideshow, right?
Ah, yes, yes. Shifted. Slide shifted. Please move to the next slide. We'll see whether it is changing.
Are you able to see this now?
Programmable logic devices we are seeing. We are seeing programmable logic devices.
Okay. You're not
Slide
seeing
number
in.
6. Slide number 6, right, sir?
No, no, no. I am not quite comfortable with this. Let me try with the. Are you able to see, madam, now?
It's the first slide again.
Slide mode. Can you see it full slide mode?
No,
Presentation mode.
it's not changed.
How about now?
Ah, yeah. Yeah, number 2.
Okay. Okay. I will change it to the full slide mode. Let me see it. Are you able to see now?
It's taking some time, I think.
The internet connection is very slow.
Are you sharing your full desktop or you are sharing only this, sir?
This slide only.
Hmm. Okay, suppose if you are sharing your full screen, then it will be, and then open this window. I think it will work. That's how we are doing.
Okay. It's not allowing me to share the full window. Let me try. That means your entire screen, right? Are you able to see now?
Yeah, number 1, first one.
Okay. Let me change to the presentation mode. How about now?
Yeah. Now, yes, sir. Fine now.
Is it okay now?
Yes, sir. Yes, sir.
Okay. So shall I start from the beginning
Yes,
then?
yeah.
Okay. So all these students are MTech students of first year, right?
Yes, MTech first year. They joined last week only, and from this Monday only we are having the regular classes.
Okay, madam. I think these topics they would
Yeah,
have
BLS.
studied it. So I will actually quickly go through them.
Yes, sir. Yes.
Okay.
Okay, fine.
Okay, madam. So once again, good afternoon to all of you. It's nice meeting you, and my name is Professor Nandakumar. So earlier I was working in the Bardiyar University, Baidas University. Then I moved to the Northumbria University. Finally, I was working in the Intel as a silicon validation engineer. Finally, I moved into the University of Nottingham. I joined here as assistant professor. Now I actually promoted to the professor. So my research interest is in digital VLSI design, defect fault tolerance of digital system, emerging non-volatile memories, particularly on memory and PCMs, approximate computing, and neuromorphic computing. Okay, so the objectives of today's talk is going to be types of programmable logic devices. This is just based on your syllabus. In the syllabus, in the last unit, they were talking about the PLA and PAL, CPLD and FPGA. So I know some of you would have actually studied about PLA and PAL and CPLD during your undergraduate and some part of FPGA also. But I'll be touching a little bit of PLA, PAL and CPLD just for the benefit of everyone. Then I'll move into the FPGA architecture, and finally we'll see more details of the FPGA in terms of programming. We will also see how to actually design so-called a bus protocols like SPI or RS-232, like serial bus protocols. And instead of actually you are actually using the bus protocols controllers, you design your own controller, and we try to implement the controller. We'll try to, first of all, we'll try to simulate the controller, and if the controller is working fine, then we'll try to implement the controller in FPGA and try to see whether the controller is working correctly. Okay. So that is going to be our end goal of my presentation. But today we will not be able to cover everything. I will touch as much as possible on PLA, PAL, and FPGA. And in the subsequent classes, we can actually go through the rest of the things, until we implement a standalone system of a bus protocol on an FPGA and test. Okay. And today's class also, I'll try to touch on an FPGA architecture, particularly on the SRAM-based FPGA architecture. And the last topic that I would like to actually give on FPGA is non-volatile LUTs for FPGAs. Of course, recently we designed a non-volatile FPGA using emerging non-volatile memory, which is Memristor. I can also share that information. Maybe this is for your knowledge sharing, and in case if you want to do a project during your MTech, probably you can actually take one or two, can take this area and try to explore it. So having said this, I would like to actually take into the programmable logic device. As I told you, many of you would have actually learned this during your undergraduate, but this is for as a kind of a refresher. And if those who did not study, maybe this forms an introduction to them, so that we can actually see that the entire class is on the same platform. Okay, here the programmable logic device can be classified into two categories. One is factory programmable and one is field programmable. Okay, so factory programmable is one which is already programmed and it is given to us. We may not be able to do anything there. Whereas in the field programmable categories, we are allowed to actually program them. So in the field programmable also, it can be further classified into simple programmable logic device, SPLD, and complex programmable logic device, and FPGAs. The simple programmable logic device can be further classified into PROM, PLA, programmable logic array, programmable array logic, and generic array logic. So in these, I think in your syllabus, they are touching on two topics, which is PLA and PAL. So I will touch those two topics before we move into the FPGA, which is our ultimate, learning aspect or learning topic. If you have any doubts, you can actually ask me during the lecture, or you can actually ask me at the end of the lecture, whatever may be that is convenient to you. So why PLDs? Okay, and it's an economical way of producing an IC in large volumes. Usually, some of the applications they may require low volumes of ICs to be developed, and it is not feasible for everyone to make an application. The reason behind it is very expensive. We need to actually make a large volume in order to make it an affordable price. So when you want like in few thousands of ICs, I think it's a better way to go for the PLDs. The PLDs can be made in large volumes also, but the cost remains the same. Okay, programmed to implement a large number of different low volume designs. So it can be applied for any low volume designs. The advantage of the PLDs are it's field programmable. When I say field programmable, what field are we going to use for programming it? Anyone can actually say? Is it possible for you to answer my question, or it is not possible? I do not know the setup there. Madam, is it possible for them to answer the question? Hello?
Sir, it's not possible. I'll ask them to pile up their.
It's not possible, is it?
Not possible. They can come. They have to come over here to my laptop and then ask.
Okay. Okay, then I will just go
maybe
ahead.
at the end
In
of the
case.
session.
Okay. Okay. So when we say here field programmable means we are going to use electric field to program it. Okay, so this can be done outside the manufacturing
Sunny, you
environment. After the device is manufactured, then we actually
if you
program the
have
device. This
doubts,
is something like,
okay, please
you
note
buy
it
a
down.
ready-made car,
Finally, you
rather
can
than
come here and
customizing car.
ask.
Okay, the customizing car is one which is called as application specific okay, these PLDs. It allows updating the device or correction of the errors. So even if you make small errors in your design, you can actually make it the corrections very fast. Whereas if you take ASIC, later I will explain to you the complete ASIC flow. The complete ASIC flow may take around like few months, maybe I can say typically 1 year to get a chip out. So to make it faster, like after 1 year you need to wait for another couple of months before you really get your device working. So that kind of a marketing the market to window time or the correction of errors is going to be very quick with respect to the PLDs. Therefore, it has a great advantage in reusing the device for different designs. Therefore, it is called as ultimately reusable. PLD is also quite often used in emulators. Probably you might have actually called as you might have actually heard about emulators. The IC design companies like Intel, AMD, they have emulators. You know about the simulators, right? The emulators are the one that are actually manufactured using a lot of FPGAs, okay, which is one of the PLD. So they have a lot of FPGAs. They implement the ASIC design on FPGA and test the design at a low frequency of operation. So this is done for to ensure that the design is working in the hardware. Okay, so that kind of systems is available. Even the microprocessors are actually tested using the emulators. So PLDs are also used in the emulators. When you talk about the PLD programming, I said it's field programming, right? When I say it's field programming, there are two. What are the types of programming it is possible? One is we can say that it is permanently we can program, cannot be erased and reprogrammed. Okay, such designs also called as mask programming or fuse and anti-fuse. Fuse and anti-fuse are something like contradictory to each other. Fuse means you need to blow out the fuse to make it work. Anti-fuse is you can actually blow out the fuse to actually work. So like it's contradictory. As far as the reprogrammable is concerned, it is volatile and non-volatile. We can classify. The volatile programming is the one that actually uses something like an SRAM. Okay, in the SRAM, if the power is lost, then you lost the data, right? So most of the FPGAs, bare FPGAs or SRAM based FPGAs. These SRAM based FPGAs, if the power is lost, then definitely you will lose the data, right? So what is about the non-volatile? The non-volatile can be erasable, electrically erasable, a flash, okay, a flash memory also. So these things are called non-volatile, where you actually store your configuration files in these type of memories, which remains to be non-volatile. The last one is called as an emerging memory. Technologies such as memory stores, PCMs, also used as a non-volatile. To be to be more practical, the emerging non-volatile memory based technology is not into the market yet. This is in the lab-based, testing, or probably we can say that it is in the experimental phase. But until like Flash, we have the PLDs, particularly the FPGAs, which are called as non-volatile FPGAs. This Flash based technology is either integrated inside the chip or it can be kept outside the chip, for you to store the data. So these are the different types of PLD programming technologies. So if you consider the PLD programming technologies, as I said, you can see that here's a fuse technology. So you fuse them to actually make it work, and you actually make them an anti-fuse to make it work. And sometimes we use SRAMs. You can see here the SRAM bit goes and turns on this NMOS transistor so that it acts as a switch. So when the data in the SRAM is lost, that is called as volatile. When it is volatile, then you will lose the data, and therefore the turning on and turning off this transistor will be lost. Finally, the floating gate transistors, where you can actually store the data and it will be there even you remove the power supply. This thing, right? So these are the different types of PLD programming technologies. So usually when we see the transistor as a switch in the PLD, how does it actually work? Okay, when we say that it stores the data, in terms of logic. Let us consider logic, which is called as, for example, consider logic here, which is a NOR gate, which is A plus B plus C the whole bar. Okay, so how does this actually work? For example, if you see here, there are three NMOS transistors. These three NMOS transistors, the gates are actually connected to A, B, C, three inputs. Okay, while the drains are actually connected to the power supply, which is VDD. So if all the three gates are actually given zero value, like what you see here, then the output will be at 1 because this offers a high output impedance. If among them, if any one of them, for example here, the C is connected to 1, then the output becomes 0. So this logic, you can see that it can replace the logic that what you can see is a NOR gate. So the entire truth table is given to you here. So for different values of ABC, what happens with transistors? The transistors, the output actually becomes 1 when all the transistors are in the off state. Okay, in the off state, and this gate is called as a NOR gate, or it's called as bubbled AND gate. Okay. So this is how we actually implement a combination logic circuit in a PLD. Okay, so you can program it in such a way that you can change the so-called the logics. For instance, if you want to convert this into a NAND gate, okay, a NAND gate, the question will be, how will you design a NAND gate using this technology, the PLD technology? So for a NAND gate, probably you need to connect all the transistors. Instead of connecting them in parallel, you need to connect them in series. When you connect them in series, then you will achieve a NAND gate, right? So you can give a try. You can draw and see how you can get a NAND gate architecture. So it all now depends on programming these transistors. That means providing the input through these transistors. If the input bits are not, corrupted, then definitely we will see these transistors will not work as we expected. Okay. The types of PLDs, we can classify them into four of them mainly. The read-only memory, okay, it has a fixed AND gates array, and then programmable OR gates. The next one is PAL, which is programmable array logic, which is having programmable array of AND gates feeding to a fixed type of OR gates. The third one is programmable logic array, which is programmable array of AND gates feeding to a programmable array of OR gates. Okay. Finally, which is called as complex programmable logic device and field programmable gate array. So in a more pictorial representation, we can see here the inputs are coming and there's a fixed AND gate, kind of decoder, and there are programmable connections which actually goes to the programmable array and output. This is called as a PROM, programmable read-only memory. Whereas alternatively, if you make these programmable connections at the input side and make the programmable AND array, which is fed to the fixed OR array, then it becomes programmable array logic. And the third connection is programmable connections at the AND array and programmable connections at the OR array, which is called as programmable logic array. So let me actually show a programmable array logic here. So the programmable array logic we have seen here, it's programmable connections to the AND and fixed OR. So if you see here, here we have an AND gate operations, okay, and then the fixed OR gate operations, right? So these are the points where you can actually make them connection. These connections can be fuse or anti-fuse connection, but this is an AND array programmable. Let us take an example now. Here, okay, a combination logic circuit with a programmable array logic. So here we have like three functions that we want to implement. The first function is F alpha, which is A bar, B bar, C, D bar plus B bar, C, D plus A bar, B, C, D. So how to implement this? For example, here we have like four inputs, right? A, B, C, D. These inputs are complemented when they go through the NOT gate. And of course, there are the partial products are here, P1, P2, P3, P4 until like P9. Okay, so we need to actually implement A bar, B bar, and D. See, that's why we are seeing here, you can see that it's A bar, B bar, and D bar. So this connects these three logic values, and there's a partial product that's equal to A bar, B bar, and D bar. That's actually fed to the AND gate and it goes to the OR gate. Similarly, B bar, C, and D bar. That is done here. You can see it's a B bar, C, and D bar. And the last one is A bar, B, C, D. You can see that it's A bar, B, C, and D. So all these inputs like partial products, three partial products, P1, P2, and P3, they are fed to this OR gate that results into this function which is F alpha. Okay, this is how we actually try to get a combination logic circuit by programming this PAL. Okay, so other functions are here, which is F beta and F gamma. We can try to get them by actually properly programming this AND array. This is called as an AND array. So why it's AND array? Because we are trying to actually AND them together. Okay, and finally we add them to here. So this OR array is fixed. We cannot do anything at this point here. Okay, only what we can do is we are allowed to change the connections at this in this array, which is considered to be AND array. That's why it's called as the PAL. I hope you can understand. Unfortunately, we could not have a discussion. I could not actually feel how you really understand this subject. But anyway, I hope that you are all understanding. I'll continue with my lecture. So next is PLA. PLA is a programmable set of AND gate combined with a programmable set of OR gate. So which means that just now we saw only the AND gates being actually programmable. Now you have an option to program on the OR gate side also. So when we have these two sides are programmable, then it is called as PLA, okay, programmable logic gates. So here we have actually different product functions, and these product functions are coming to here. You can see the product functions P1 to P7, and we can program this OR array in such a way that we can get the final function. Okay. And we can take the final function at the output here. So here you can see these are the product functions, and when you see about the OR gate here, there are three OR gates, like it provides the function F1, F2, and F3. The F1 actually adds this product function and this product function, this product function. So you can actually choose whichever the product function you want to add, and then you can choose this OR gate, whichever the OR gate you want to get the output. Therefore, it is programmable both in the AND gate array and also in the OR gate array. Okay. These are the early versions of the FPGAs. FPGAs did not actually start, along with these. So earlier we had, this kind of programmable logic arrays that finally resulted into FPGA. Maybe this also can give you an idea how the technology evolved to the latest technology of SoC. Okay. Here is an example of binary to gray code converter using PAL. You all know how the binary to gray code converts. And here I put the binary code and also equivalent gray code. Okay, and if you actually draw the so-called the K map, and you should be able to get the gray code versions for the given binary values. So then you can implement in this PAL. So why I'm showing here is it is possible even to implement this kind of converters using this programmable array logic. Okay. Then I'm actually moving on to the CPLD. Since we have seen this PAL and PLA, now if you look into the CPLD, it is complex programmable logic device which involves a lot of PLDs, inside. The PLDs can be PALs or PLAs. Okay, with a programmable interconnection structure, and it is pioneered by Altera. So if you have a complex lot of programmable devices in a chip, okay, with the interconnects which are running across them, this actually works as a logic block and IO block. Then this forms a CPLD, and this is from these actually we evolved into the so-called your FPGA. Okay. So FPGA is a field programmable gate array, okay, which has high logic capacity with a large distributed interconnect structure. It actually offers more narrow logic sources, okay, while the CPLD offers a logic resources of a wide number of inputs. Okay, offers a high ratio of flip-flops, because so far what we have seen in the PLD, we can implement only the combination logic circuits. But when we move to the FPGAs, we can even implement both sequential and the combination logic circuits. Right. When we compare the CPLD with the FPGA in terms of gate numbers, you can see that the FPGA has more number of gates when compared to the CPLD and then SPLD. SPLD, as I said, it is simply a PLA or PAL. Okay. So how does this FPGA architecture look like? The FPGA architecture looks something like this, right? This is for the pictorial representation. Okay, if you really open the FPGA, is it looking like this? It is not going to look like this. This FPGA architecture is called as SRAM based FPGA architecture. So this FPGA architecture, you can see that there are logic blocks that you can see, small square blocks, an array of square blocks. In between the array of square blocks, there are wires, interconnect wires that are actually running through these blocks. And these wires and these blocks, okay, and then there are IO blocks. On top of this, there are also other blocks, okay, that we will see in detail in the next slide. Most interesting part is this complete setup is fabricated as a chip and given to you. Okay, and in this, what is most important is we are allowed to configure the length of the wire, okay, and the routing of the wire. Also, we are allowed to configure the logic blocks, and we are allowed to configure the IO blocks. So almost everything in this FPGA, bare FPGA, is configurable. Okay, so which means that you can change the design, or you can implement different designs in this FPGA architecture, so that you can actually realize your design in a hardware. Okay, so the question can come to you: how it is possible after you fabricate a device, okay, it becomes a silicon, how can you actually configure the wires? How can you configure the logic blocks? Okay, what is the technique that they are using to actually configure the logic blocks? Okay, are we going to use AND gates, OR gates, and all these basic gates? And if we use all the basic gates, how are we going to connect them through the wires? So that's going to be a question for you, right? Maybe you may have this kind of questions. Let's see more detail out of it. Before going to address that point, let us see, more detail about this actual FPGA architecture, which is Xilinx Vertex 2 architecture. Okay, if you see the Xilinx Vertex 2 architecture, it has got similar to what I showed in my earlier slide. It has got programmable interconnects, IO blocks, okay, and then configurable logic blocks, which is called as CLBs. Okay, configurable logic blocks. On top of that, it has got clock management units and dedicated multiplexers. This is very interesting. Dedicated multiplexers are the multiplexers which they claim to be having zero delay. Okay, and then the block selected RAM resources. There are RAM resources also inside. So as such, this bare FPGA, okay, doesn't have any processor inside. Okay, any processor inside. It has got the configurable logic block, which has got the element of both combinational and sequential elements. Okay, so using configurable logic block, you can implement the complete digital design, which comprises of both digital and with comprises of both combinational and sequential logic. Okay, of course you can actually route using the programmable interconnect. You can use the multiplexers and SRAM. So which means that this bare FPGA, you can see that it is going to execute everything concurrently. Okay, but the question may come whether you will be able to implement a processor inside this FPGA. Yes, it's already possible. There are there are already some of the IPs available. These processors are called as soft processors. Okay, so even Xilinx actually released the soft processors where you can implement inside this FPGA. There are FPGAs which comes with ARM processors inside. Okay, and this can actually work like a SoC. Okay, system on chip. Okay. Now let's try to understand a bare FPGA without any processors, okay? And what are the different, elements in that, and how they can be, how we are allowed to configure them, okay? That's going to be a more interesting topic, okay? So before going to there, what is this FPGA and why it's been, so popular, and where are they actually used? FPGAs have been used, almost everywhere, like in aerospace defense, automotive vehicles, data centers, medical, smart vision, ASIC prototyping. This is what I was talking about. Okay, which is called as the emulators, audio, consumer electronics, industrial electronics, smart networks, security, wired communication. You can take any area people are using FPGAs. Nowadays, the FPGAs companies also being bought by so-called the big companies like Intel and AMD. So main players in the FPGAs are Xilinx FPGA, Altera FPGA, and Actel FPGA. I think Altera has been already bought by Intel, and Xilinx is also being bought by, if I'm not mistaken, by AMD. Right. So in between, like Xilinx and Altera, they have a certain architecture which I'm going to explain to you. The Actel FPGA will also I'll explain to you. Actel FPGA is something like which is hardened FPGA, which means that it is used for mostly the space application. When these two companies like Xilinx and Altera were in the market, they were the main players of the FPGA. Okay, Altera was having a small segment of share in the FPGA share. So when we talk about FPGA, as I said, it's low cost for low volumes. If you have like few thousands, it's much better to go for an FPGA. But you have like few million chips that you want to implement, it's better to go for an ASIC design. Okay, and it's reprogrammable and quick time to market. The quick time market is very important, because when you come out of the design and you need to have you need to bring it that design into a chip and sell it in the market as soon as possible. Otherwise, your competitor can actually take over the competition market and they can sell the product. For example, if I say that I have a processor which is like Pentium 5 processor, which can actually work excellently without any errors. Nobody is going to actually buy now, because we are actually moving towards multi-core processors now, right? So which means that we need to capture the market. If someone is saying about USB 2.0, people are not going to bother about that much. So the new designs need to bring it to the market as early as possible. But what is the problem here bringing the new design? So when you want to bring the new design must be bug free. How can you make it bug free? You need to have a proper design, and then you need to verify the design. Okay, we will see several steps how to verify and what are the things we need to do. Okay, so it is quick time to market. It's because even if you find there are some errors in your design, you can quickly reprogram the FPGA and get it ready. Whereas for ASIC, it is going to take a lot of time. Therefore, it's slow time to market and low cost for large volumes. Why it is so? Okay, let's see the ASIC flow of implementation. If you broadly see that ASIC flow, ASIC here means application specific integrated circuits. So usually broadly it can be classified into the behavioral level, which is like specification. Whenever you have some kind of a problems, like the market requirement, then the market requirement will be converted into specifications. Okay, the specifications will be a document, that document will be looking like for instance like a textbook. Okay, like a textbook. For instance, I don't know whether you are able to see. Maybe at the end of this lecture, I can show you the document for USB. Okay, it's kind of a specification. When the specification is done, we convert that into the RTL level. By using HTL programming, we can actually convert it into the RTL level, and that's further converted into logic level, and then to the transistor and to the layout. Okay. During this process, I have actually broadly classified. During these processes, we need to actually have a lot of testing methods to ensure that the design is working fine. The design, you might have designed very well and it can work fine, but when it is been actually working with a high frequency, sorry, different temperatures, okay, all these things has to be verified, and a good chip manufacturers will spend a lot of time in testing. Once you get your idea into layout, the chip is not going to be ready, because this layout is supposed to be given to the fabrication. So if you give to the fabrication, even if you take a multiprocessor wafer service, you can see that the GDS2 file goes for masking. First of all, the mask is created, and then its fabrication process is started. Okay, and when it enters to the fab, then after they do all sorts of fabrication, different fabrication methods, which I'm not touching out now, and then it is going. The wafer will be coming out. After the wafer is coming out, then the packaging will be taking place. Okay, and then we get the chip, and this chip with package or without package, you can say this process alone can take 12 weeks to 16 weeks, which is roughly 4 months. Okay, and if you design from here to the layout, if it takes nearly like 7 to 8 months, easily it can take like that. Okay, so if you add this, you can see that for your design to get into a chip, it takes nearly 1 year. Okay, so at the end of 1 year, if you discover that hey, something is wrong in my design, Okay, so I missed something in my logic circuit to fix it. So what will happen now? You have to go all the way back to the logic. Okay, there are two types of bug fixing. One bug fixing is at the chip level itself. At the chip itself, we can remove the layers. I do not know whether you studied VLSI design, but we can see that there are two levels. One is the silicon wafer. On top of them is the metal layers. So we can actually chip out all these metal layers, and then we put metal layers once again. So these metal layers are the one that makes the connection. Whereas the bottom layer, which is called as silicon, which has got all the transistors. Okay, so if there are problems with the metal layers, we can try to actually chip out the metal layer and lay the metal again. But if there are a problem with the base layer, then completely we need to throw away the wafer. So this process will take almost like 1 year. And if you end up seeing that you have made a problem in terms of your logic design, then we have to say that we lost the market. Not only losing the market, the money that you spend on these engineers as a salary, and also as for fabrication, will all actually go waste. So when I say that it goes into this fabrication process, it already will actually cost few $1 million. Okay, so you can see that this product is not easy to market, right? Whereas let us take this FPGA flow. Now you design something in the HTL code, okay, or schematic code, and then you actually synthesize it and get the net list, okay, and then you generate a bit file and implement into the chip. So if you find that the design that's on the chip is not working perfectly, then of course you can go back to the design. Sorry, you can go back to the design, and you can fix the design and again implement on the FPGA board. So how long it is going to take to implement the design on this FPGA board or FPGA chip? It's going to take only few seconds, right? Hardly few seconds. So when we compare this design flow with this design flow, which takes 1 year, I think this design flow is more easier, more quick to market when compared to the ASIC flow. Okay, that's why the FPGAs are becoming very famous. But you should understand, whenever we say something is very attractive, then definitely it will have its own drawback also. Okay, the drawback of this FPGA flow is that it is not custom made. So in terms of speed, or in terms of area of the chip, it is not optimized. Okay, when as compared to the ASIC design. Okay, therefore its performance will not be on par with the ASIC for certain applications. So that's going to be the challenge, or that's going to be the negative part of these FPGAs. But of course, some applications where you don't worry about the area or power dissipation, okay, critical applications we are not going to use, then of course you can always choose FPGAs. Right. A more detailed thing that you can see is you need to plan and budget for the FPGA flow, and create a schematic or HDL, do a simulation, synthesize, and after you synthesize, you do a functioning simulation. So this one you will do, when you do the lab, definitely you will be doing an HDL simulation, and you synthesize it and do the functional simulation. Functional simulation just ensures that your design is working for the given function, but it did not actually really test whether your design is working for timing. Okay, even though you synthesize it, you will get some kind of a gate delay. Okay, gate delay. So after you get the gate delay, even if you do the functional simulation, there will be some delay information inside. But if you do a simulation at HDL RTL level, there won't be any actual delay involved in here. Okay, so that means only the functional simulation is done here. A little bit of timing simulation is here. Okay, but not a complete timing simulation. Why it's not complete timing simulation? Because these are you are using only the AND gates, but you did not know how you are going to place these logic gates. Okay, that's why we have this implementation phase where you have translate, mapping them, and placing and routing them. So after you translate, map, and place route your designs, then you get a complete footprint of your design onto an FPGA. If you get a complete footprint, that means all the routings and everything, then you can actually you can get a complete time, and this timing will be equivalent to or this kind of a model or design will be equivalent to same as it is in the hardware. So if you see that a design is working well after you do a place and route, then that means the design most likely will be working on an FPGA. Okay, so that's a concept. But if you see that a design is working on HDL RTL simulation, you cannot expect the same design to work on an FPGA if you implement it. Okay, some people actually they write the HDL code. They don't even do the simulation. They just implement the HDL code directly into the FPGA and expect the FPGA to work for them. Definitely, it will not work. Okay, like 99.9% at first instance, none of the code will work on an FPGA. Even with the simulation, will have a really a tough time. Okay, so when you write a behavioral simulation, here we call this the design as technology independent, technology independent, because we don't put any so-called the timing information, or it is not tied with any particular FPGA design. Okay, once you synthesize, then the design becomes technology dependent, where it depends on the on the transistor, or the transistors that are used for manufacturing the FPGA. Therefore, the delays associated with that is will be taken care here. And after that, placing and routing all becomes technology dependent. So you cannot take this design at this stage and then implement it to another FPGA. Okay, whereas you can take a design here in the RTL level, and you can implement it to another design. So finally, coming to here, right? After you attain your time simulation timing closure, then you can generate the bit file, and the bit file is the one that's been actually implemented into the FPGA. So all this process has been done inside the inside your computer. Okay, using the tool that's provided by the FPGA vendor. Sorry, FPGA manufacturer. So when I say plan budget, there are two design entry methods for HDL. One is architecture wizard, core generator, or static CAD tools. Which method you will use? You will need to tool generate the EDF file or NGC. Okay, file links implementation. So for example, if we want to actually take the final file and then create a change, make changes, it's still possible. Okay, right. So I think this one I actually covered just now. And timing closure, there are several methods that we need to see the proper timing closure. Okay, this one I'll take it up in my next class. But meanwhile, I am actually move into the FPGA architecture itself. So now we understood what is the difference between an ASIC and an FPGA architecture, right? ASIC and FPGA flow, and we have also understood how this FPGA is evolved from simple PLD to a complex PLD and to an FPGA architecture. So basically, as I told you, the FPGA architecture has got configurable logic blocks, which is CLBs. Okay, and then input-output blocks. Okay, which has got different methods like double data rate registers and digitally controlled impedance providing on-chip terminations. So we'll see them. Okay, and this configurable logic block has got lookup tables to implement the logic and storage elements for flip-flops or latches. On top of this, it has got block RAM providers for data storage and multiplier block. Okay, and digital clock managers. So we'll see one by one. Okay, first the CLB. CLB is the configurable logic block. Usually, if you see a typical Vertex one, it has got 4 slices inside. Okay, the 4 slices are connected to a switched matrix. Okay, these slices they hold both combinational and sequential logic. Let's see what is inside this slice. Inside the slice. Within the CLB, the routing is called as the so-called is local routing. Okay, so if you take a slice, the slice has got a slice. It has got LUT and some flip-flops like D flip-flops. Okay. And sometimes it has got some kind of multiplexers also inside. So the main important design here is two. One is LUT and flip-flop. The LUT is called as lookup table, and this lookup table is used for designing any combinational logic circuits. Okay, whereas the flip-flop is used for designing any sequential logic circuits. So if you have both LUT and the flip-flop, then you can design a digital circuit successfully. Okay, let's see how this LUT works first. Okay, before we move on into the so-called your D flip-flops. This is an actual slice. This one I'm showing a piece of slice, but if you take actually, it has got a lot of multiplexers. You can see, okay, and these are called the dedicated multiplexers, okay, and some carry logic and multi-and and sequential elements, like two of the sequential elements here. This is showing like 4 input LUTs. There are 2 LUTs. Both of them are like 4 input. Okay, right. So how does the lookup table work? Okay, when I say this lookup table here, we try. I said that it is used for storing the combinational logic circuits. So let's consider this combinational logic circuit, which is A bar B plus CD. We want to implement this in the lookup table. Now, how does this actually work? So basically, if you think it has got 2 AND gates and then one inverter, one OR gate. So this is how we actually try to draw, right? So we will be drawing like this. It has got 2 AND gates, one inverter and one OR gate. But actually, if you take the Xilinx or Altera FPGA, it is actually implemented in terms of lookup table like this. What is important here is the ABCD are the 4 inputs. You can see here, and Z is the output. These 4 inputs actually acts like an address line of a memory. This is very important. Okay, why it is very important? Then you will try to understand why the delay through the LUT is constant. Okay, the delay through the LUT is constant. So we'll come to that. Okay, why? Let me see whether I can. Laser pointer, yeah. So why the delay through the LUT is constant? Okay, we will consider these, the so-called your inputs. So 4 inputs are there. Therefore, 16 possible combinations are allowed. Okay, and Z is like 16 bits. Yeah. For each one possible combination, there is 1 bit. Therefore, there are 16 bits available there. Okay, right. Having said this, the total memory size of this circuit or this LUT is 16 bits. Okay, it has got 4 input address lines. 4 input address lines. So which has got 16 possible combinations. So what are we going to do now? Okay. So let us take, let us take 0, 0, 0. That I'm actually writing a 0 here. For 0, 0, 1, I'm writing a 1. Okay. 0, 0, 1, 0, I'm writing a 1 to this memory location. 0, 0, 1, 1, I'm writing a 1. Like this, I'm keep on writing the values. Okay. I know if I give the A, B, C, D values, right? So I'm supposed to get some value for Z. It can be either 0 or 1. Okay. So if I give 0, 0, 0, then definitely it is going to be, you can see here 1. So 0, 0 is going to be 0. Therefore, Z is going to be 0. So it's going to be 0, right? So like this, we know what are the values of the Z. And this value of the Z is been actually stored in the memory location, 16-bit memory location. For instance, that you want to actually provide a value for ABCD input value. Okay, let me say that in my input for ABCD lookup table is 1, 0, 0. For this combination logic is 1, 0, 0. Where A is 1, B is 0, C is 0, and D is 0. Then immediately I will get a value of 0 as output. Where this 0 is stored, it is stored in the memory location. What is this 1, 0, 0? This is called as address. So you go to this address and fetch the data from the memory, then you get your output. So which means that you can clearly see that we don't use any OR gate or AND gate and an inverter in this design. We are just using a kind of a memory to actually emulate these combinational logic circuits. So when you use a memory, every time we need to go on, read from 1 bit. So when you want to read from 1 bit, then for all these combinations, you can see that the delay through the LUT is going to be constant. If you really do in terms of combination logic circuits, you can see that the worst case path is going to be A inverter OR gate followed by AND gate and reaching this Z. That's kind of a worst case path, right? So this is kind of a worst case path, all right? So whereas here there is no worst case path. The best case path is C OR gate and an AND gate, or D OR gate and an AND gate. But here the delay is going to be constant. It's because you are implementing everything in the lookup table in terms of a memory. Okay, I hope you understand this. All right, let me take you through the next one. So how are these lookup tables connected? The other important thing is that you want to make changes to this logic circuit. Okay, want to make changes to the logic circuit. For example, you want to remove that inverter here. For example, instead of a bar plus b dot c dot, this is called as a bar b plus cd, right? Now you want to change this to this function, which is a bar plus b dot c plus d. So when you want to do this function, then definitely you need to actually change, this so-called your design, right? When we compare to this design, here are two AND gates, and here you can see the two OR gates. Okay, in terms of logic connection, but in terms of lookup table or memory design, you just go and change the value at the memory location. Okay. So that's how the lookup tables are used for implementing the combination logic circuits. So if you have 4 inputs, you can implement any type of combination logic, with the 4 input, with the possible 4 inputs. You can see there are 4 slices, how they are actually connected. One slice output is connected to the next slice, and the next slice output is connected to the following slice, and it keeps going on. This is how the slices are connected, interconnected inside a CLB, and finally the output is taken out. Okay. Next, I want to talk to you about programmable interconnects. Okay, so now we know that the CLBs, right? The CLBs consist of both logic and both combinational and sequential logic. Sequential logic actually is using only flip-flops. There's nothing much there. So the combination logic is using the LUTs. Now, after you design this CLB, then probably these CLBs, you can see here the logic cells, these are called CLBs. These CLBs need to be connected. They are connected through the wires. Okay, these wires are so-called wires, or called programmable wires, and it's called as programmable interconnect. So you may wonder how the wires are programmable. For example, let us consider that there are 4 logic cells CLBs. So you can see that there are a number of wires going horizontal and there are a number of wires going vertical. Okay, when the vertical and horizontal wires are crossing, that's where we have a kind of a box which is called a switch matrix. Okay, and inside the switch matrix we call this programmable interconnect points, which is PIPs. PIPs. Okay, so what is this PIP? The PIP is nothing but kind of an NMOS where the gate is connected to the SRAM cell, which means that depending on the value of the SRAM cell, this NMOS will be turned on or turned off. For example, if you want to turn on this particular NMOS, right? So the SRAM must be 1. It must provide a 1. When it provides a 1, then you can see that the current that is flowing through the wire getting routed and goes to this particular SRAM. And here it goes into this wire, and then it reaches this logic cell. So basically, the value in this logic cell is transferred to this logic cell by programming these SRAMs 1, 2, and then 3. Okay, so this sort of programming is called, by doing this programming like this, it's called as programmable interconnect points, and that's why this entire network of wires are called as programmable interconnects. You can see that actual diagram I can show you in the next. Oh, sorry. So here you can see that actual connections. How does it look like? We call these as line segments, nets, and programmable interconnects. You can see that here you can show that configurable bit goes to a single transistor, and it's represented by a circle here. Okay, if you have this circle here, you can connect this internet to this, or this wire to this wire. Similarly, if it is in the cross junction, you can connect either the horizontal wire or vertical wire, or from horizontal to vertical. Okay, this called as cross point. And switch box is something like this PIP, where in a cross junction we have six transistors. These six transistors, they actually try to route the signal from one end to the other end. For example, if you see my, you can see my arrow clearly here. So when this particular transistor is turned on, then the data from here actually goes to this another end. So by configuring these transistors, we can ensure that how the data can be flowed through these. And this structure is called a switch box, and it's otherwise we call as programmable interconnect points. You can see a lot of them here. This is actual CLB, and you can see that these are the programmable interconnect points through the wires. So these wires can be actually classified into long wires, quad wires, which is like 8 wires, very lengthy wires. Okay, and it's also double wires, single wires. Okay, and global wires. So we have a lot of this type of wires. These wires plays an important role, particularly in terms of your delay. Okay, and therefore we need to see the delay aspect also. Some of the wires, like so-called your global wires, usually will have less delay, which means that if you send a clock through the global wire, then the jitter because of the clock will be very less. Okay, so usually people prefer use these global wires to send the clock signals, right? So that's about the programmable interconnects. So now we have actually studied about our we analyzed about two things. One is about the combination logic blocks, and another one is about the so-called the programmable interconnects. Okay, now having known these, right, so next we try to attempt to know more logic blocks inside. Okay, the next logic block inside is fast carry logics. Okay, simple, fast, and complex logic circuits. So these are called dedicated OR gates for a single level sum combinations. So why we use this? To perform some kind of an adding operations. There are dedicated OR gates apart from the logic gate. Okay, they use dedicated routing also. Okay, so you can see the slices. Okay, and on top of that, we have a dedicated XOR gates. You can see dedicated XOR gates. So these are actual XOR gates. These are not the XOR gates that are coming from the LUT itself. Okay, multi AND gate. Okay, so highly efficient multiply and add implementations can be performed using this multi AND gate. Earlier FPGA architecture required only 2 LUTs per bit to perform the multiplication operation, but the multi AND enables the extra area reduction by performing the multiply and add in 1 LUT per bit. So which means that you can do both multiplication and addition in a single LUT. Okay, here we have an LUT in terms of AND gate, and then it goes to the LUT, and finally it gets an multiply. And we have a flexible sequential elements also. The flexible sequential elements are either flip-flops or latches, as I described earlier. 2 in each slice, 8 such CLBs are there. The inputs coming from the LUTs are from an independent CLBs. Separate setup and reset controllers are available for these. You can see that set and reset when enable equal to 1, and this is called as when enable FP. This is the flip flop, right? CPE and clear. There's another LD CPE is also available. The next thing that what we have is double data registers. The double data registers can be clocked. Okay, we have 2 registers, 2 flip flops, and by a clock or not of a clock. So we use a clock here and a not of a clock. So which means that it is going to actually increase the data rate. Okay, by doubling the data rate, one for the clock and one for the not of the clock. The clock and not of clock, if the duty cycle is 50 by 50 percentage. Okay, we must have a duty cycle. By clock 0 and clock 180, the outputs from the DCMs can be obtained. Okay, if D is 1 and D2, D1 is 1 and D2 equal to 0, the output is the copy of a clock. Okay, IO buffers. So the IO buffers also going to become interesting. At the input path, there are two DDR registers. Okay, and the output path, there are two DDR registers as well. Okay, a separate clock and enable for IO is provided. Set and reset signals are actually shared. You can see that this is a pad. Before going to the pad, there are registers. Okay, for the output, and this is kind of an enable signal. So we can actually try to provide the input and also try to get the output from the pad. Okay, so it can actually work in both ways, like input and also like output, depending on the enable of this buffer. Finally, we have this, the block selected RAM resource. Okay, probably we'll be using one of them during our project. Okay, so so here we have a dual port memory. So this is kind of a block memory which is inside the FPGA itself. Okay, this dual port memory is designed such a way that we have like two ports, and in these two ports we can write and read from one port to other port, or we can actually write and read from the same port as well. So which means that we can perform the write and read operation from one end to other end, or from the same memory as well. This is going to be very useful when you want to store the data. For example, when you are actually writing the so-called the protocols, right? As I was telling you, the bus protocols, then probably you need to fetch the data and store the data. For that, we can actually use this kind of memory devices. Okay, right. So this is another important block, which is called as dedicated multiplier block. Okay, this dedicated multiplier block, if you want to really use some kind of an higher end applications, and these dedicated multiplier blocks, which is already implemented inside the FPGA. Okay, which receives like 18 bits of A data and 18 bits of B data, and it multiplies. We can also choose like 4 by 4 signed, or 8 by 8, 12 by 12, or 18. We can configure that. Okay. This is what I was talking about, like global clock routing resources. So you have a clock pin. Okay, when the clock pin goes through the wires, definitely they may actually go through a so-called your skew. Clock skew can actually occur. So in order to avoid the clock skew, there are a lot of buffers being provided. That is a traditional way. Okay, these buffers actually try to ensure that the clocks are having the same delay, which we call also as clock free generator. But here there are wires, okay, that is designed in such a way that the clocks are reaching to the resources without so-called your clock skew. Okay, so if you try to use a clock, I think the global clock routing is always better, because that gives you the so-called less delay, and less so-called the less delay in terms of rise time and the fall time. Okay, which means that you can rely on the clock. If it is going to fail for the rise and fall time, naturally it is going to fail for the timing simulation. Why it's going to fail for the timing simulation? Because there's a timing margin for setup and hold time. This setup and hold time are not met because of there's a delay or skew in the clock. Then definitely your design may fail in the timing simulation, even though your design can pass in the RTL level, in a logic level, but when it comes to timing level, it will definitely they fail. Okay, so it is better to use this type of the global routing resources. So I will talk about the other FPGA vendor, which is Altera. They use also the lookup tables, and then carry logic, and there's a flip flop. Okay, they call this as a logic element, instead of CLB. Okay. Okay, the next, the vendor, which is like Actel, they do these kind of FPGAs, but they use so-called as, the fusing mechanism, anti-fuse mechanism. They want to connect two wires, then there's a fuse. They blow up the fuse, then they make the connections. So by and also the logics inside the Actel itself is multiplier based circuit blocks. I will actually explain what is multiplier based circuit blocks maybe in my next class. Okay, we use multipliers to actually get the combination logics, and to connect the wires we connect using antifuse. So which means that it is not using any lookup tables here, so which is using dedicated hardware. So when you want to change the design, then the hardware design need to be changed. That is about the algorithm, Actel. Sorry, Actel. So when you want to select an FPGA, right, you must look for different systems. For example, you want to implement some kind of a design, right? So you want to look for, what should be the size of the FPGA, just, and how many gates are there, and what are the number of CLBs, block RAMs, and IOs. So most importantly, at least we must know how many IOs are there and how many IOs are free to use. Okay, so then only we'll be able to implement a design on any design on an FPGA. Okay. Here I'm showing an example of SOC, where this SOC has got a lot of processors. This is not a bare FPGA. This is an FPGA that has got both fabric FPGA, of fabrics of FPGA. Along with that, it has got ARM processors. You can see the ARM processors here. So along with that, it has got other features like USB, Gigabit Ethernet, and UART, CAN, I2C, SPI. So it has got a lot of features inside apart from the FPGA. So this system is actually used for implementing the complete system. Okay, right. So we can also customize the FPGA boards. For example, you have FPGA, you can actually design your own FPGA board. This is one of the FPGA board that we have designed for our university. All right. So we can come out of the PCB and we can design our own FPGA board. That also will give you a really a good experience for the project. Okay. Now it is, I think, we are almost 1 hour 15 minutes into this lecture. So at this point, okay, I will stop here. Okay, we have actually covered some of the FPGA architecture and some of the elements inside the FPGA architecture. We also covered what is CPLD, and what is so-called your um PLE and PAL. Okay, we also discussed about what's the difference between ASIC and FPGA implementation. Okay, now I stop here and let me know whether you have any questions.
Yes, sir. I just ask whether there are any questions. See, you must be having some questions, right? So much of because there is no interaction possible in between. It's a continuous lecture. So questions. Do you have any? You must be having questions. What is what at least, right? Yeah. Yeah. Questions. Any questions? You will first tell me. Then you can come here. What is AUT? How it's working? Have you understood? And how it is working? How it is working as a combination logic? Okay, and then programmable interconnect you have understood. Yeah, anyone, if you're having questions, you can come here and ask. Anything, it may be anything. Anyways. Hello. Yes, sir. They are right now not having questions.
Oh, is it because they learn all these things before, or really they understand or don't understand? I do not know.
No, no, they have a fair idea. Somewhat they know the basic things. LUT and all they are saying they know already.
Mhm.
PLA, all those things you have studied. Okay, some of them they have studied.
Okay, there are students who also did not study about these topics in the class.
Yes, sir.
Are there students in the class they did not study on these topics?
Are there
Because
any?
I am trying to go according to the syllabus.
Yeah, any students who are not who have not studied these things before? See, it is. Uh, yeah, anything that's any term which is new to you, you can just ask. Yeah, there should be somebody, someone. Please. It may be very basic question also.
Okay, I think let's not actually, embarrass them.
Okay.
But what I feel is that if these topics are already being covered because it's in the syllabus, so I'm actually forced to touch these topics. If it is, if there is something that additionally we can do something, then probably we can do it. So that we can make the class, more. The learning can be more. Not
Okay.
duplicate same thing that already they studied.
Sir, so do we have an? Please keep quiet. So do we have? Are you continuing or we are finished?
Can we have a break now, madam? That means we'll stop here. And I think it is what time you want to stop here? No, maybe you said.
I
Uh,
have a class. Around 3:10. If we stop, close the session, it will be
3:10.
easy for me.
3:10 means how many minutes left over?
So then there will maybe we can have 10 more minutes and wind up. Otherwise,
I think at this stop, maybe I will touch a little bit on non-volatile LUTs. Maybe interesting for them.
yes.
Is it okay? Okay. So, are they actually done any programming with the FPGA boards, or are they new to that? Are they done any HCL designs and implemented them on an FPGA?
Say they have just had one class, one lab class. They have done just adders, basic adders in Verilog.
Okay, okay, madam. But in their undergraduate, did they actually do anything on FPGA implementation?
Undergraduate, some of them have done.
Okay,
Some of them have done, sir.
okay, okay,
Not everyone.
okay, okay. So I will quickly go through then on the non-volatile FPGA LUTs.
Okay, sir.
Hello, for another 10 minutes, right?
Yes, sir.
Because your voice is not hearing to me clearly, it's breaking.
Yeah, if we are, see, please keep quiet. Yeah, shall we continue now and finish by 3 o'clock or 3:05, sir? Because having a break and again starting may take time.
No, it's not having a break. You are asking for another 10 minutes, right? I will actually cover some topic.
Okay. Yes, sir. We can have
Okay,
10 more minutes.
okay, madam. Are you able to see my screen, madam?
Yes, sir.
Hello.
Yes. Non-volatile LU.
Okay. Yes. So just now, for another 10 minutes, I will actually touch on this topic, which is called as non-volatile LUT, right? So in this non-volatile LUT is kind of a design that we came out in our lab here. Okay. We use the device called as memristors. Memristors are the devices which is so-called um, uh, memory plus resistor. Okay, so this is one of the non-volatile emerging non-volatile memory that can actually store the logic states by moving the ions inside the structure of the memory device itself. Okay, here if you see on your right hand side, on top of the right hand side, there are like crossbars, and these crossbars are called as nano crossbars. These nano crossbars, when they have both horizontal and vertical lines. In these horizontal and vertical lines, the horizontal lines are called as the word lines, whereas the vertical lines are called as bit lines. So when the word lines and the bit lines they cross, at the cross junction, we have the memristors. So these memristors, if you see how does it look like in terms of using electron microscope, you can see that it looks like platinum, titanium oxide, and platinum. This is called as a MIM structure. Okay, in this MIM structure, we have 31 nanometers for platinum top electrode, 50 nanometers of the bottom electrode, and 26 nanometers of the titanium oxide. So this structure is being placed, and if you see actually the design, it looks something like this. This is a bottom electrode and this top electrode. Okay, so when you have this kind of structure, we try to actually emulate the same thing in terms of circuit, in electrical circuit. We put like 4 of the memristors, and these 4 memristors are connected in such a way that there are 2 horizontal lines and 2 vertical lines. As I said, the vertical lines are called bit lines and the horizontal lines are called as the word lines. So the word lines are connected to a controller where AB is the 2 inputs of the LUT. Okay, and there's a read enable, write enable, and reset. So AB is 2 inputs, therefore it's possible for you to actually store the functionality that whatever that you do with the 2 inputs. Okay, this is a simple structure, but you can extend it for like 4 inputs also to replace non volatility. How does this actually work? Okay, when you see, for example, when you write to this word line, when you choose M11, right, we can write to this memristor. Okay, the remaining memristors you will not be able to write. So when you write to this memristor, you can change the resistance of this memristor from the high resistance to the low resistance, or low resistance to the high resistance. So by retaining this resistance value, we are retaining the logic states. Okay, so by retaining the logic states, when we remove the power, the resistance level of this memristor remains as such, and that's how it actually stores the logic data. Okay, for instance, you can see here, when you want to write a 1, right, we provide a VDD. When we want to write a 0, we provide a minus VDD. Okay, so which means that it depends on the memristor itself. For example, when you give a positive voltage, it changes from the high resistance to the low resistance. But for this particular memristor, when you give a negative voltage, it actually does the opposite value. Okay, therefore we use both values of VDD and minus VDD to write a 1 and write a 0. Okay, to read a 1, again we provide the positive and negative voltage, but the read pulse is going to be very, very small when compared to the write pulse, because the read pulse is, again, we are going to send the same voltage to the memristors to read. Okay, we introduced kind of a new write and read methods. This is a new write and read methods. Okay, using VDD and negative VDD. Okay, and the transistor controls are selected by means of the transistors here. If we choose T1, right, we provide a supply to the T1, and T1 turns on. When T1 turns on, then probably you can see that the M11 and the M12, or say M21, they are connected to the ground. Okay, so depending on whether you provide a voltage to WL1 or WL2, that particular memristor will actually change its value to retain the logic value, right? So if you change this, if you actually turn on this T2, then you can actually program M12 or M22 depending on the value of the voltage that you apply on the WL1 and the WL2. Okay, so this is how it is going to actually work. By selecting the transistors, we can try to actually write to the desired memristors. Okay, so no data monitoring circuits. Previous write and read operations, they were using some kind of a data monitoring circuits to write a 1 and 0. They actually changed from the bit line to the word line and word line to the bit line. That's been completely eradicated in this method. Okay. Um, So even there's no refresh pulses required. I can actually show you the characteristics here. Just one second. Yeah. So this, I think, yeah, this is kind of a control circuit. Just one second. So I think probably just give me a second. I hope you can actually see the screen now. So what you can see here is there's an applied voltage. Okay, this about this design. Just now I was showing you. So when there is an applied voltage, okay, applied voltage you can see from here from minus zero point 0.9 volts to 9 volts. So when there's an applied voltage that is here, then what happens to this NSP? NSP is the state of the memristor itself. The state of the memristor actually changes from 0 to 1. You can see that the memristor state actually changes from 0 to 1 and reaches to the maximum value of 1. That means that ions completely actually move to the other end and it is conductive. Okay, this is called as your complete write cycle. So after you write a cycle, then you can actually apply a small pulse. You can see here a small pulse, which is called as a read pulse. So this read pulse reads the state of the memristor and provides you the output. Okay, this output can be observed here, across this point, T1 or T2, it can be observed. Okay, when you want to give a write a negative value or zero value to the memristor, then probably you need to change from plus VDD to the minus VDD. That was what I was saying here. Either provide VDD or minus VDD. So if you give a negative VDD, then what happens is you can see that the NSP actually goes from 1 towards to the 0, right? It goes to the 0, and then you can see when you apply a negative voltage here. So when it goes to 0, and it stays there. So when you want to read the 0 value, again you provide a small pulse to read the value. So this small pulse, the read pulse, actually tells what's the state of the memristor. But unfortunately, the small pulse actually tries to pull the NSP to a little higher value, not making it to go to the original value, because you are providing a positive pulse, right? This positive pulse makes this NSB to be going to the higher level. So to actually bring it back to the low level, then we again apply a small negative pulse to bring it to the low level. But unfortunately, it is not going to the low level completely. Okay, so when you retain this, and probably this may give you an error, because if you keep on reading it for multiple times, then you will see this negative value will not actually make it to come to the original value. Therefore, it can accumulate, and it can end up that this value of NSB can reach the maximum value also. There's possibility like that. Okay, but we analyzed it, we analyzed it, and we find that the NSP is not reaching to the maximum value. It actually stays at nearly 0.2 or 0.25 volts. Okay, and we also analyzed with a different pulse width. We use different pulse width for the read pulse width: 10 nanoseconds, 5 nanoseconds, and 1 nanoseconds. In all the cases, and we actually run for a quite long time, we found that the value actually restores, and there's no big change in terms of the state of the memristor. Therefore, this design, we can actually use it for actually storing the logic values. For instance, that you want to actually use two inputs, right? Data 0 and data 1. So you want to actually store for instance, like 1000 like this, it can have like possibility of two inputs, which is 00, 01, 10, and 11. In 00, you want to store either 1 or 0. So if you want, 00 refers to the memory register M11. Okay, 01 refers to the memory register M12. Similarly, 10 refers to the memory register M21, and 11 refers to the memory register M22. Okay, in these four memory registers, you can store the logic values. It can store 4-bit values, right? So if you actually store a value here in the M11, and the M12 and the M22 and M21, that means you change the resistance value of these memristors. You change the resistance value of the memristors, and now you remove the power supply, the resistance value remains same. So that's why it's called as non-volatile lookup table. Okay, so this non-volatile lookup table, even when you actually take it anywhere without power, the design that you implemented in the lookup table will actually stay as such. Okay, so more about this probably I can actually present to you during my the next class. Okay, now I think with this I will actually stop here. Okay, uh, and let you allow and allow you to go to the next class. I think it's 10 minutes now already. Is it 10 minutes, madam? Already
Yes.
we crossed 10 minutes.
Yes, sir. Yes. Hello.
Hello, we is it 10 minutes now, or we
Yes,
have
sir.
some more time?
Yeah, yeah. I, we can wind up, sir. I think we can wind up.
Pardon me, madam.
Yes, sir. Can we wind up now?
Okay, madam. Okay.
Okay.
So I thank you all of
So
you for listening to the lecture. Okay. I hope to see you on another class. So probably we can understand more about this FPG, and also we'll try to design some of the bus architectures.
yes, sir. Thank you. Thank you very much.
Thank you, madam. Thank you.